Hello and welcome to the Network Forensics Analysis Talk. My name is Rami Al-Talhi. I am Senior Incident Response Consultant at Cisco Talos Intelligence Group. For today's agenda, we'll be talking about a couple of topics. We'll be starting with defining the network forensics, what it is and what it does. The second topic for the tools and platforms that is available and can be used widely. The third topic, we will be talking about the dilemma with some encrypted protocols such as TLS, SSH, RDP, etc., and how we can overcome those challenges. And the fourth topic is for real-world APT, Advanced Persistent Threat Attacks scenarios, where they are using and utilizing some encrypted protocols such as DNS over HTTPS to hide their compromise. So let's start with network forensics definition. I have found a good definition in Wikipedia for network forensics, which says it's a sub-branch of digital forensics relating to the monitoring and analysis of computer network traffic for the purpose of information gathering, legal evidence, or intrusion detection. So network forensics is a branch of digital forensics beside other host, memory, mobile forensics, etc. And once we combine a network forensics with other datasets like host or memory, we would generate a good visibility and investigation journey. All right, so a couple of tools and platforms we have to perform the network forensics analysis job. The first tool, which is very commonly known in this field, called Wireshark. Wireshark is a tool to read and filter and investigate any PCAP file or trace files. If you have a PCAP file, the first thing you go into Wireshark to just look into what's going on as a conversation. Also, you can look into statistics. You can look into endpoint, etc., as we will see in the next slide. It has another version called T-Shark, which is a command line version. It's really a useful tool if you are looking into a scriptable option for this tool. TCP dump is exactly as T-Shark does, but it is based on the PPF filter, and also it doesn't understand application layer. It is much faster than, let's say, T-Shark in reading huge PCAP file, but it has a limitation to understand layer 7. So that's why the speed comes from. Sometimes you need to swap between them. So you need to use TCP dump to slice this packet back and send it to the Wireshark or T-Shark and vice versa. Zeek is a fantastic tool to read the metadata of most of the protocols used in the internet, things like TLS, SSH, RDP, HTTP, whatever protocol is there. It has ability to read it and also to provide you with information, things like if you look into TLS, like the issuer, also it provides you with the hash, etc. For the IDS, sometimes we are looking into scanning the PCAP without going into the details. So we are looking into signature-based detection rules, things like Snort, Suricata. It is a good option to have to pass the PCAP through the IDS. So you can just install Snort or Suricata to scan your PCAP. Network Miner is a nice tool to visualize the PCAP. You are just importing the PCAP into this tool, and it will provide you all the information without knowing anything about the PCAP. Just going through the tabs, and you'll see much and tons of information. For example, if there is any picture being traversed in clear text, it will be available there. You can see, export, look into that picture. The same for the password, etc. Okay, so let's look into the network forensics challenges. So we got a couple of network forensics challenges in here, which have a big impact into the network forensics investigation. also for network monitoring for any environment. We will discuss about those points and how we can overcome each of them. We'll be discussing a couple of challenges that might limit the ability to investigate the network traffic. The first one is inventory assets. Before collecting the packet capture, we need to have a list of inventory assets. If we don't know, for example, where is the critical service or servers that we are aiming to have the packet capture out of it, we will not be able to collect it and acquire it or even monitor it. So if we don't know the asset that we have, then we don't know what to protect and what to monitor as well. The second thing is the network baselining. Baselining here we mean we need to understand our network very well, especially in terms of throughput, also the protocol being used, a couple of statistics that we have, and we will see an example in the next slide. Encryption. So encryption is the most challenge that we have in network detection and investigation side. Things like TLS, SSH, RDP, and other protocols, other encrypted protocol as well. The attacker now utilize things like DOH, which is DNS over HTTPS, where they hide their traffic based on this protocol. So we'll see how we can utilize some tricks and tips to understand the pattern of the attackers. The last thing is the data sources availability and usability. We need to have the data sources to be available and usable. So both of them need to be existed and in place. If you look into the CIA cybersecurity control, you will see the control number one is inventory and control of enterprise assets. So this put the priority number one for this inventory assets. So figure out your assets that matter. Can be application, can be servers, can be services. So find out the important and the critical mission of your business. Then after that, you have the all information about them. Make sure it's protected, make sure it is monitored. So in this topic, we'll focus on the monitoring and investigation as well. So finding out the inventory, having the inventory in place, having all the details about them, patch them, backup them, test them, all these very critical information and critical mission to have in your environment. Find out the pattern to find abnormalities in our network does need a network baselining. We can look into our protocols traversed our network. We can look into the throughput. We can look into different statistics to find out those metrics to identify the maliciousness of the traffic in our network. For an example, for the packet length, we can look into the DNS. If the packet of the DNS length exceeded that amount of identified packet length, that means we need to have to receive alerts and it should be a red flag. Also, the duration, the same goes for payload entropy. If it's higher, that means it deserves an investigation. Egress and ingress, as we can see here, we can identify exfiltration. In this picture, we can see from the 8th of January, we have spike until 400. So that means we have seen abnormal traffic, especially in the weekend. It's not in office hours. And also we can see a different protocol, like a protocol that we are not using for huge amount of bandwidth. So a lot of use cases actually can be built over those four category. Let's jump into network profiling, and we can use this network profiling especially for the encrypted traffic. As we discussed earlier, the network traffic has a big challenge for the encryption. Most of the protocols we have used today is encrypted. If you look into the HTTPS, for example, it does use TLS. RDB used TLS. We have SSH, which is encrypted. We have many protocols is encrypted by default. Also, these encryption actually it's limiting the ability to for the investigation and monitoring, but still we have some ways and workarounds to find out the malicious traffic over there. And we will discuss about GA3, which is a way to identify and profile the TLS traffic that initiated from the host machine. Also for GA3S, which is the same as GA3, but this is to identify the servers. The third one, JARM, is a way to identify the servers, and we can actually categorize the servers based on their TLS mechanism, as we will see in the next slide. We have hash and hash server, which used for SSH fingerprint. If you look into SSH connection, for example, and you are connecting from your host or laptop into the server, actually those connections can be used to identify you and or identify anyone from the connection of the SSH, as we will see. The RDB, remote desktop, it does use TLS, and we have very interesting information about it to find out the user that being logged into that RDB to identify the attacker activities as well. The community ID is a way to profile the, let's say, the net flow. So it's actually a hash value being generated for the flows itself. More details in the next slide. So talking about GA3 now, it's a way to read actually the hello packet of the TLS handshake, as we know. And as you can see from this picture, actually GA3 will calculate a couple of fields from TLS hello packet and will provide you with MD5 hash. Those MD5 hash should indicate into specific client. This profiling actually being built by Salesforce team, and actually they are doing a very fantastic job to determine the way to profile these encrypted packets, as we will see J3, J3S, and hash as well. So how it works, actually, it does calculate MD5 hash value based on TLS version. If you are in 1.2, if you are in 1.3, it does it has some different hash for those values as well. So any value being changed in those parameters, it will accordingly change the MD5 hash as well. Accepted ciphers, list of extensions. So if there is more extension or less, those will affect by the calculation as well. Elliptic curve and elliptic curve format. All of these should be actually matched to have a same value of the MD5. The same goes for J3S. S here means the server. So J3S, the difference between J3 and J3S. The J3 actually looking into the client hello TLS handshake, where J3S looking into the server hello, since we are talking here about the server. So from the server side, it will calculate 3 parameters in TLS only, not like J3, as we have more than 3. So in here, in J3S, we are looking into TLS version, accepted ciphers, list of extensions. That's it. We don't have elliptic curve and etc. So it will look into these 3 parameters, and it will determine the MD5, and it will calculate the MD5 hash for you. So it should be unique. We have here some of useful use cases for identifying J3 and J3S fingerprint. If we look into, for example, profiling Tor client and also Tor server, what we can do actually is looking into J3 fingerprints. For an example, this is the hash, MD5 hash of J3 of Tor client of some previous versions. where you can actually do some threat hunting and to build some use cases. If you have a SIEM, if you have any dataset that you are looking to that does have J3, then you can just look into the HAYSTACK for these hashes, and also you can generate your own. Absolutely. For J3S, it's the same for the server. If someone like just running the Tor as a server, then you can look into the fingerprint for this hash as well. Some attacker actually manipulate these values, as we will see in the next slide, so we can discuss this further. Another example is here for ransomware families. So we have TrickBot and Emotet. One of the things that you can look into the ransomware, you can look into the client. For an example, J3, we have TrickBot, communication TLS, and also we have the C2 server response. So this is the C2 server response of the attacker server backend. The same goes for Emotet. So you can see how useful is J3 and J3S for identifying the malicious traffic in your environment, either from the client side or from the server side. Both should be actually useful to identify those, and you can investigate this further looking into other datasets and also for those endpoints which actually generate those communication and connections. Now let's jump into some search engine for J3. We have actually two websites in here. The first one, j3er.com, where it provides you with a search capability, Google-like search engine, where you just paste the J3 value and you can identify what is this client actually or the server. So this is the first website, and we have another website in the next slide. This is another website. You can look into abuse.ch, J3 fingerprint, and you can look into specific J3 after you are looking into, for example, if you have a list of J3 fingerprint, you can look into them, and it has actually a good function or good feature here to list for listing reason, where it does label by the malware family. If you look into the first hash here, we have TrickBot and how many malware samples being submitted into this website. Also, it shows you some timestamp for the first scene. So it's really make our life easier by looking into the J3. Once you have this implementation, then you can just figure out what client is connected to what server from the TLS, even though if it's version 1.3 where there is no host name being embedded with the TLS, since it is encrypted, not like 1.2, etc. Now, enough talking about J3, J3S. Let's talk about impersonation. So, can the attacker now manipulate and impersonate the J3? Absolutely yes. It's impersonated and it has been seen in the wild. So changing the cipher suite or TLS version will change the J3 completely. As we have discussed earlier, we have a couple of elements for TLS like TLS version. If you just change that, if you just change some extensions, adding, removing, then this will be changed accordingly. Other factors needed to tackle this issue. So what we can do to tackle this issue, we can look into other datasets like other TLS characteristics and extensions. Also for host correlation. If you have data from the host itself, you can just correlate it with the host event as well. One of the things that you can utilize in PowerShell to manipulate and impersonate the TLS is to use enable TLS cipher suite command. Then you can position an extension as we have here called TLS DHE DSS into lower priority. So changing the priority or the position of specific TLS cipher suite will change and impersonate the TLS accordingly. So attacker might use this way or another way to just manipulate TLS, and this is just for demonstration. You can manipulate the TLS, any TLS actually extensions to change the MD5 fingerprint of the J3. There are a couple of limitations for identifying J3 and J3S fingerprints. One of them is these fingerprints merely based on the TLS cipher suites. So it doesn't look after the cipher suites. Also, it doesn't look into the different TLS characteristics, things like ALPN, which is application layer protocol negotiation. It doesn't look into it, and it doesn't look into anything else than these TLS characteristics, which is already determined from the previous discussion. Also, this makes the J3 not very unique, and some clients might share the same MD5 fingerprint. Bear in mind that these MD5 fingerprint might match with other. So there is a percentage or some false positive within the J3 and J3S. So this should be considered once you are doing or building the use cases and doing the threat hunting or investigation. Can be manipulated by changing the cipher suites extension. As we have seen from the PowerShell, you can just manipulate it with lowering or position the TLS into a different position. So J3 and J3S is good tool and good mechanism to trace the TLS, but it doesn't provide you with accurate and let's say clear answer if this fingerprint is for X client or Y, but at least it provides you with some context surrounding the use cases that you have. Salesforce team actually built recently JARM fingerprint. So this is, let's say, another level that we have for TLS fingerprint. But the main differences between J3 and JARM is made by live scanning for the servers, and it's just considered for the server, while J3 and J3S is a passive tool where it calculates the MD5 fingerprint for client and server. So JARM actually is an active transport layer security TLS server fingerprint tool. It is active, so you need to interact actively with the server to collect these JARM fingerprint. So scanning with the JARM provides the ability to identify and go malicious server on the internet. You might have a couple of servers. Let's say you have a load balancer and you have a couple of servers behind that load balancer. If you go, for example, in Salesforce or for Google, they have a lot of servers to serve the clients. But using the JARM, you can have a unified fingerprint can indicate this fingerprint just related to a specific company or a specific provider, as we will see in the next slides. We can use JARM to quickly verify all server in group have the same TLS configuration. So it's really looking into the TLS configuration to identify the server of groups. As we said, Google, Salesforce, you have multiple servers might share the same TLS configuration. Those servers will provide you with a single unique fingerprint of the JARM since they have shared TLS configuration. So also it's group disparate servers on the internet by configuration to identify the server might belong to Google or the Salesforce as we described earlier. Also to identify the malware and C2 infrastructure and other malicious server on the internet. You might have the JARM fingerprint for the C2 backend, so you can utilize JARM to actively scan the servers and identify those TLS configuration. So here we have two different examples. We have the Salesforce servers and we have Google servers. We can see in the upper of this picture we have implemented or executed the JARM Python script to the Salesforce team, salesforce.com, and also we have force.com. Both of them shared the same TLS configuration. Now we have a single unique JARM fingerprint where it indicate into the same TLS configuration. So we are looking and we are dealing with the same entity. Also, the same goes for the server of the Google. We can see Google and YouTube, they are sharing the same TLS configuration. So it's really provide you with a context about what you are dealing with, what kind of the servers that we have, even though we have a different IP, as you can see in this picture, but still we have the same TLS configuration and we have the same unique JARM fingerprint. Now let's look into the RDP or remote desktop protocol. We know that RDP is encrypted by TLS, and there is a couple of ways that we can deal with RDP to unleash and discover more information and pivot into different data points that can be beneficial for the investigation. Looking into the RDP protocol in Wireshark, for an example, you can see clearly what user being used during the RDP session. If you look into the image and below, you can see in ASCII format that we have cookie equal testing. So the testing is the username being used. So I just use this in the lab, and I have used the user called testing just to show you that we can capture this information. And this is very critical information. You can utilize your SIEM to do threat hunting based on specific users. Some attacker used or create their users in the systems, so you can track those users using the cookie field in the RDP. Now it's the time for SSH fingerprint. We will see how we can identify the SSH connection, how we can identify the client, the server. We can identify even the operating system being used by the client and server as well. Salesforce team have developed hash and hash server to identify and fingerprint the SSH connections for the client and server. So it's exactly as JA3 but for SSH. So it is MD5 hash value from the set of the algorithm in SSH protocol after TCP handshake. So we have TCP handshake in first hand, then we will have SSH connection and transactions. So from these connection, hash server and hash can be calculated based on the algorithm called SSH message keyexenet. It's transferred in clear text, so you can read it without encryption. So it's being transferred from client to the server in clear text. You can look into, for example, in Wireshark. It does include the server and client application strings, as we will see in the next slide. Couple of benefits using hash and hash server. So we can utilize it to attribute a SSH connection with greater accuracy than only by IP. We can log into the connection and application being used for SSH. For an example, if you are using POTI, if you're using any other systems, or even in Ubuntu or any Linux machine, and you are using the terminal, we can identify those as a user agent. So we can see the client version and operating system as well with the server version of SSH and the operating system. One of the things that we can utilize hash and hash server is regardless of the NAT devices. So if you have a couple of workstations being compromised by attacker, what we can do is we can look into the SSH string or hash server and hash. So we can log into the client and the server regardless of the NAT devices, as we will have these SSH connection being captured and hashed by those two algorithms. It's analogous to HTTP user agent. So You can use it as HTTP user agent in a web browser, so we can identify SSH version, if it's version 2 or anything else, or they are using OpenSSH or any other different um, uh, tool, then we can identify the operating system. Let's discuss about client and server SSH communication and how it's being done. So once the client needs to communicate with the server in SSH, first place will have the TCP three-way handshake, and after that it will have SSH communication. We can see from this illustration we have server identification string, client identification string, where everyone from client and server will send their strings, which is user agent like in HTTP or in browser. These strings actually contain the SSH protocol and the client, also the operating system. We can see we have OpenSSH and Ubuntu as a server, and we have OpenSSH and Debian or Raspberry Pi from the client. So after that, we have SSH message keys in it, two message, one from the client, one from the server, and both of them can be used to generate the hash and hash server fingerprint MD5 value. We have two sections here, clear text and encrypted. So clear text can be utilized by the fingerprinting for user agent like for the string from the client and server, and also SSH message keys in it for hash and hash server fingerprint. The encrypted part is for the data payload, where it's encrypted and it's not visible for the man in the middle. Looking into the hash algorithm from the client, how it's been happening from the Wireshark practically, we can look into the packet called client key exchange initialization, and we can see the value. So the below value actually used to generate the MD5 value out of the hash. So the hash actually will be calculated from using these values for the client and the server. From the next slide, we will see how this is being calculated from the server side. Here is how the hash server calculates these values from the server key exchange initialization, and it has different value where it will be used to calculate the MD5 hash for the hash server. So now we have hash and hash server, where we have client and the server hash value. We can use it for our threat hunting in our environment to see who's communicating to who and in what client. So we can see the operating system, the client, and also the endpoints. We can look into SSH client string, which is in another bucket. So from the client side, we can see clearly here that the client used SSH version 2, OpenSSH for Windows 7. So we can map that with our SSH and SSH fingerprint as well. Now we'll be talking about the HAYSTACK dilemma. So if you have been in a situation where you have a lot of PCAPs, let's say over 500 GB, and you have been asked to investigate for any maliciousness within those packets. So it is not an easy task to handle. So we have a couple of ways to show you how you can handle such situation and what are the things that you need to consider in prior to go within this investigation. First thing that we need to look into is slicing and merging. What do we mean by that is by defining this, the right scope. So we do have a timeline and we do have an overview about the incident or about the case that we need to look into it, or also the threat hunting. So we have a couple of things that we can look into, or also we have source IP, destination IP, anything that can be filterable. Then we can just shrink the time, or we can select specific any criteria that might align with our investigation. In this case, if you have, let's say, 1 terabyte of packets, then it will come down maybe 80% less or more than that if we have the right information in hand. So one of the things that we can use is to use EditCap. So EditCap is a tool already packaged with the Wireshark. If you install it in your machine, then you can use it to slice the packet based on the time. For example, if we need to specify the start time and stop time, we have a specific timeline. We can use -A capital or -B, and we can use the format as described in this slide to identify the timeline. So we are interested to look into, let's say, 1 week ago, then we can specify the timestamp based on what we have from the scoping. Another way to look into the PCAP is by splitting the single PCAP into different PCAPs based on specific amount of packet. In this example, I have used editcap-C1000, which means that you are telling the editcap to just count the first 1000 packet and throw it into a single file, then start from that. So what I'm doing here, I'm reading tcp.pcap, read the first 1000, throw it out into the current folder, and just do this continuously, and throw that into tcp_analysis.pcap. As you can see here, we have a list of the PCAP files. Every and each file have 1000 packets. This is very useful to split it out into a different PCAPs where you can look into just small amount of packets. And also it's very useful to use different tools, so it's easily loaded into your tool, things like network miner and etc. Now a time to merge all them together. So what we can do actually is to merge the needed result out of the PCAPs that we have analyzed into a single PCAP. So merge cap, then -w, which we mean that we need to output into the single file which called out.pcap, and we can also combine them with all the output or all the splitted PCAP we are looking for. So A.pcap, B.pcap, both of them will be merged together into a single file called out.pcap. What we can do actually after we have these analyses to use some IDS, things like snort or suricata, and here I have used snort to read the file.pcap and reading the configuration called snort.conf-l to show you the result in the screen. So snort actually is an IDS, has a lot of signature built in. You can develop your own. You can also have some community rules, or you can purchase any snort signature, or you can use suricata, which is available all publicly in the internet. Then you can scan the entire PCAP to look into any match with signatures that available from the snort. We'll be talking about two APT use cases utilized by a different attacker group that being reported publicly, and how the attacker utilized different protocols to evade the cybersecurity controls and even to be hidden in their network traffic. The first case is for DNS over HTTPS malware, which called DOH, and the attacker here used DOH to evade all the cybersecurity detection tools and network monitoring systems as well, and we will see how they are deploying their malware and what to do about it. Let's first look into the DOH and identify the main characteristics of this protocol. So it is DNS over HTTPS, and it's used by 443 TCP as if it was TLS, and querying DNS using HTTPS protocol. So there is no more 53 UDP protocol or traffic in here. Also, we have more privacy, and it does make security analyst job harder by investigating these traffic, since it is fully encrypted and blindly passing all the cybersecurity monitoring tools if it's not using any man-in-the-middle decryption. So a couple of browsers supported it, like Firefox, Chrome, etc. So advisory here, welcoming DOH to hide in the HAYSTACK. So attacker loves actually to have evasion over any cybersecurity monitoring tools to hide their track and also to mislead the cybersecurity analysts. First malware sample we'll be looking into is 6-spot, where the attacker actually used their code to use DOH, which is DNS over HTTPS. So we'll be looking into their code and how they are utilizing DOH to achieve their objectives. This is the snippet of the malware code. In the first square, we can see that two domains being encoded by RC4 format, and both of them, both of the domain actually ending with .hk after you decode it. And the function which is in the other square, we have DOH. So actually what this function does is looking into or resolving those domain using dns.google.com, where it does support DOH. And also they are actually using type A, where they can translate to the IP. We will see how this request being done from the next slide. So the attacker actually used the DOH heavily in this sample just to do the DNS lookup for those domains. This is the other snippet that we can see demonstrate that how the DNS resolving have been handled. So we have a GET request into dns.google.com that asking to resolve this domain which ending with .hk, the type A, which is one of the types that DNS have, to resolve this domain into the IP. And we can see the JSON format in the below section. We can see the IP have been appeared for us after resolving from the Google, which starting with 119.2.8.4.8 and 231. So attacker successfully accomplished their objective by resolving the DNS of their domain after decode their domain from the malware code from the RC4. They are doing the resolving using dns.google.com, and they can accomplish their objective later on. We have another use case used DOH in different way. So the attacker here can actually download a malware binary from the internet using DOH, and we will see how this have been accomplished. Also, we will see how you can see and look into this in Wireshark. The first thing you will notice in Wireshark that the server name, which is dns.google.com, from the HTTP traffic. So this is actually the decrypted from Wireshark, where it does show you that the dns.google.com being communicated using HTTP to resolve specific domains. Here we can look into the full picture where the attacker used get command into dns.google.com to resolve mimikatz domain using text record without using DNSSEC, which is set to false. And we have the full URI in below. We can look into the full URI here, and we can see the user agent of the attacker where he is using Chrome version on Windows. Once he did that, you can look into the full payload in here. You can see this payload started with TVQ, and this is base64 format, and anything in base64 format starting with TVQ, usually it does indicate that it is a binary. So the attacker successfully able to retrieve the payload in base64 using domain over HTTPS or DNS over HTTPS using just HTTPS traffic. So the analyst, when he log into the traffic, he will see HTTPS traffic and he will not be able to see all these information. I would like to thank you all for your time, and I appreciate you have been here, and it's the time for the questions if anyone have any questions.